Good evening, everyone, and welcome to the Carolina Weather Group. We're happy to have you this evening, and we have a really special guest on with us, Dr. Karen Kosiba. She is it's hard to explain what all she does, but we had one of her coworkers on, Josh Werman, a few years ago, or maybe last year. I can't remember. All the days run together now, but Karen works with Josh with the Doppler and Will project, but is also doing a lot of other things in the weather community and research community for improving our weather models and warning systems and all of that. So we're excited to have Karen joining us tonight. So Karen, first time guest, so we'll give you the opportunity to kind of introduce yourself, but we always ask this question to our first time guest. How did you get bit by the weather bug? I mean, what was that one particular moment or storm that really is like, that's what I want to go chase, or that's what got you interested in weather?
You're supposed to ask me my favorite color, much easier. I certainly was always fascinated about weather growing up, but I can't say I was ever totally into it. I sort of was more into photography and engineering type stuff, and I did physics when I went to college, and then I think eventually I was thinking there's a lot of unanswered questions in atmospheric science, and some of the stuff I was looking at in physics, I was sort of surprised that I'm like, oh, really? People don't know this, or people are still trying to figure this out. I'm like, oh, you could not sit in front of a computer all day, and you could get in the field and do this type of stuff. So I think some of that naturally attracted me to weather. I was always interested in the extremes of weather, so I like tornadoes and I like lightning. And it seemed like tornado stuff, just that was the path. That was the path that had more things going at the time I was sort of deciding between the two.
Talking about tornadoes, and I know you've been a part of a lot of research programs, and one that really caught our attention, kind of like why we reached out to you, first of all, was the PERiLS. I think I'm pronouncing it. PERiLS
Yes.
project, which is you're going to be studying QLCS tornadoes, and
Correct.
that is something that we see a lot of here in the Carolinas. And for those who are not watching, we can talk about what a QLCS tornado is. But it's something that's really dangerous, and they happen at night, and they're rain wrapped and all of that stuff. And so pretty important topic to research. So tell us a bit about this project.
So in terms of QLCS tornadoes in the Southeast United States, and I won't get into too much, but there's supercells, which are sort of these big isolated thunderstorms that rotate, and not that we understand them well, but we understand them more-ish, and we could give sort of longer lead time and prediction with them. But these QLCS tornadoes happen, they're part of usually these longer systems, or sort of these broken systems. And they're more common in the Southeast and in the Carolinas. And they don't have much lead time. So warnings associated with these don't have much lead time. They do happen a lot of times in off hours. So after dark or early mornings, times people aren't really expecting tornadoes. And that's the big motivation for this project. So again, we're looking at this in the Southeast, and we're trying to really improve forecastability of these type of events. So we're going to be looking, we have, this is a National Science Foundation funded project and a NOAA funded project. We're going to have 6 or 7 mobile radars out there. We're going to have 8 or 9 sounding teams. We have 6 or 7 profilers. We have 5 or 6 mesonettes. We have 40 plus weather stations that we're placing in front of these storms. So what we're going to be looking at is the environment in front of these storms. So what's the environment like in front of these storms, and how is this environment evolving? So are there clues that anywhere in this sort of really favorable region that might be more prolific in producing tornadoes in these long storm systems? And then we're also going to be looking at the storm system themselves. So with these radars, we're going to be scanning low levels, we're going to be scanning fast. And we're going to really be trying to understand rotation, the development of the rotation of these storms, and seeing if there's precursors to this rotation linked to this fast scanning or this low level scanning that might help with forecastability. Again, there's a really hard time forecasting tornadoes in these systems. So we're going to be doing it March and April this year in 2022. And then in 2023, we're going to go out again. We're going to go a little bit earlier because these storms in the Southeast really don't have, I mean, there's still this sort of March, April-ish peak, but they definitely have trailing on what we'll call the cool end of the season, which are your Januaries, Februaries, and even Decembers for that matter. So we're trying to get a little bit then into that. So we're going to start a little bit more into February in order to capture cool season parts of these storms.
Severe weather season in Southeast is growing.
Yeah.
It used to be in the springtime, but now it can happen wintertime, springtime, fall time. And obviously we get our summer pop-up storms that can go severe, but that tornado season runs from fall, winter, and spring now. And we're seeing more and more often these systems develop. So one thing I want to ask you, you've been involved in this, or you're going to be involved in this, and you've been involved with several other tornado projects. And we're getting really good in tornado forecasting and warning, but what are those things that we're still missing? What is this research for that you guys are going out there? I mean, what is it you're still trying to learn about tornadoes?
Yeah, so it depends which project. So the QLCS in the Southeast, I mean, I think it's still I think it's much more challenging to forecast these QLCS tornadoes because either we're not scanning low enough with our 88Ds, we're not really understanding how the environment's evolving. Again, we're not observing it enough, to understand that. So I think QLCS tornado formation is lagging behind supercell tornado formation. So I think there's a lot more to be learned from that. I mean, supercell formation, again, these are big rotating thunderstorms, and most of those don't go on to produce tornadoes. But we could at least see the rotation and understand that these storms are rotating. So even if we issue, even if the National Weather Service is able to issue a warning because it's rotating, that's more than you could actually do for a QLCS, because we're not seeing that fast enough, or we're not getting the precursors fast enough for that. And for all tornadoes, I mean, what intensity tornado is going to form and how long it's going to last for is always up in the air. And I think it makes a difference in some ways. I mean, in terms of, people should always be taking precautions when tornadoes are forming, when tornado warnings are happening. But certainly the difference between, an EF5 tornado and EF1 tornado, that's significant in the types of damage that you'd expect. So being able to know a little bit better, hey, again, I'm also saying you should still be taking precautions, but certainly you might be taking slightly different precautions if you know that an EF5 tornado is going to impact your town, or that the tornado is going to, the tornado that's happening 20 miles that way is still going to be happening, 20 miles that way.
One of the projects you've worked on is Doppler on wheels. Such a cool little thing, the DAOs. Can you tell us what a DAO is? And kind of what it's like to operate one? So
the DAOs, the Doppler on wheels, have evolved a lot since they were initially invented by Josh Berman back in 19-diggity-doo. I'll just say I was in high school, so I make myself feel better in this whole thing. No, but they're radars that basically were put on trucks initially to start out. And the idea, and he had done that initially to get close to tornadoes. So basically it's putting a radar on a truck, and the idea is that you have a nice radar and you drive up really close to what you're studying. And then when you're really close to what you're studying, you can see things in fine scale detail, you could scan fast, you could do a lot of different things. And like I said, they've evolved. We're dual pole, dual frequency. So we have some fancy type of signal processing and transmitting and receiving that we do. And we have 3 trucks, somewhat like that. And then we also have a new radar that we did. It's called the COW, which is the C-band on wheels, which is kind of, it's like a DAO, but not quite. So DAOs, basically we just drive up to anything, start scanning. We scan sometimes when we're driving. The COW takes about an hour and a half to set up. It's C-band, so it has a larger dish. It's a larger wavelength radar, and the dish is in 2 pieces. And on site, we assemble it with a crane, and then we're able to use a C-band. And the idea is that with a C-band is a longer, more penetrating wavelength than an X-band. So you're able to see through storms better, things that have hail cores, stuff like that. You're able to see through that better. But the disadvantage is, of course, in order to get the same resolution as a DAO or an X-band radar, you need to have a bigger dish with those bigger wavelengths. So that's why we have to assemble it on site. So it's the only radar of its type, which is pretty cool.
We saw your little video on Twitter and the two DAOs that you have running in tandem there.
Oh, yeah.
And what exactly was going on there? What were you trying to accomplish, and what are you trying to do with like meshing those two radars together, I presume?
And they're going to be doing synchronized scanning. So we were basically out today with the two X bands, trying to just program in the scans and making sure that they're working and that the data looks good and stuff like that. So they're going to be doing something called dual Doppler analysis, which basically is two radars that are scanning and looking at the same spot in the same instant in time. And from that, what you could do is you could do 3D wind retrievals. So if you're familiar with single Doppler, like your 88D or something like that, you're looking at what we call radial velocity, which is meaning that any component that's parallel to the radar beam. So whether it's completely parallel or not completely parallel, or zero, which means that you don't see anything. With dual Doppler, you have two different perspectives. So you get the U, the V, and then you also get the updrafts and downdrafts associated with the winds.
Quick question on that one is, are you doing vertical profiling as well on the winds, and for how high up do you go?
Yeah, so we'll do something called RHIs. So we're going to interleave for this project. We'll do a bunch of volumes that are dual Doppler synced, and then we'll do RHIs, which are basically, instead of horizontal cross sections, they're vertical cross sections through the storms.
So this brings to mind another question, Karen, and it's what's it like actually operating the DAO? I'm kind of a weather geek myself, so I'm geeking out here too. What is it like to do this, and how does it compare to using the WSR 88D or TDWR? Are you doing like volume scans, or is it just one cut and you're done with looking at a particular elevation, or can the radar just do whatever you want?
Yeah, no, that's a good question. So I've never operated an 88D, although I think it would be good. So we could do whatever we want with that. So in terms of scanning, so we're very flexible. Nothing, a lot of times for these projects, and especially if they're not our projects, so if we're not the actual, scientists sitting there on the radar. So for example, for tornado projects, I'm sort of switching stuff like on the fly a lot. A lot of times for projects, and even sometimes when we are PIs, we sort of have these canned scan strategies because we're working with 5, 6, 7 other radars from other universities or other institutions. So you could scan, how you want to scan. So you could do volumes if you want to do volumes. You could interleave RHIs into those volumes. You could just scan vertically if you wanted to. You could also, change the pulse length. So you could change, how long of a pulse you're sending out. You could change when that pulse comes back, how often you want to sample it. You could change your PRT. We do staggered PRTs or single PRTs where you interleave a short and a long PRT, which increase your Nyquist. So it increases the velocity you could see. So whether you see 20 meters per second as the unambiguous, or whether you see 80 meters per second, you could change that type of stuff. And again, it just sort of depends on the project and what people are interested in. In some ways, in the ADAD also sort of does this too, and there's a reason for that. Well, the ADAD is operational, so it's looking at stuff. But for projects, a lot of times you do sort of want to do, repeat scan things, for a long time, just because, you're trying to get lots of data to understand something. So you don't suddenly want to do this and this and then this and then this and then this, especially if you have several radars out there. Sometimes with one radar, you're like, yeah, let's go there, let's go there, let's scan there, let's scan there. So a lot of times there is sort of, I'll say, a can scan strategy, but there's a lot of free parameters in doing that. The other thing we have, and this you'd have to decide beforehand, is our two DAOs and two of our DAOs in the cow are dual pole radars, but they're also dual pole radars that transmit in 2 frequencies. So traditionally with a dual pole radar, you transmit in, one frequency, whether it's X, C, S, and you transmit a lot of times in 45, which means you have a vertical and a horizontal. And you just do that in 1 frequency, but we do that in 2 frequencies that are independent of one another. So they're just slightly offset, but slightly offset in a good way. So that makes us able to scan faster. So we get a lot more independent samples, which is good for dual pole and reflectivity type products. So we're able to scan faster a lot of times. The other thing is we could do different things with those different frequencies. That was my different things now, but one could do 45, and we can get the 45 suite of products, which people are familiar with, your ZDRs and your row HVs and stuff like that. But then we could, with the other frequency, transmit, say, in horizontal, and then receive back in horizontal and vertical, and get something called LDR, which is another product that you can't get if you're just transmitting in 45. But it requires some switching of our plumbing through the radars. So that was a really long answer about
yeah,
that
sure
was an
was.
ADHD.
And I'm sure a lot of it went over some of the general audience's head here, but I will add in a couple things. PRT, that means pulse repetition time, which
Correct,
is how
yes.
frequently pulses of the radars go up. Not everybody realizes that it's not just a steady beam coming out of the radar, but it's a lot of rapid pulses that are on the order of milliseconds. Or actually nanoseconds, really. And then there's a listening time that's
microseconds or nanoseconds usually,
in between. So anyway, and changing that pulse repetition time allows you to either get better reflectivity data or better velocity data. I can't remember which one longer gives you better velocity, and which one being longer, and which one gives you, or the shorter one gives you better reflectivity. I can't remember which one, but is which. But that's the reason why you do that. Why you vary that pulse repetition time is because it gives you better velocity data, or gives you better reflectivity data, depending on which one.
Yeah, and again, what we do is we do a stagger a lot, which means that we're transmitting at two different pulse repetition frequencies, and other people do different types of ways to do that to get basically, better sensitivity, but also higher Nyquist or higher velocity data. So there's certain ways to do that, but I mean, we have a lot of control over that. So that's sort of, we could,
Right.
hopefully not break the radar.
Yeah, and the National Weather Service radars kind of do the same thing. They'll do one scan with a certain PRT to get good reflectivity data, and then do the same tilt again to get good velocity data.
Correct. But we do that all at once. So with a stagger, you kind of do that all at once. So I think that, it's always hard to get. I think some of the Weather Service radars, I think they're sort of going towards a stagger. They're trying to implement a stagger as opposed to a one scan and then a one scan, because you lose temporal.
Yeah, it'd be nice to do that because you'd reduce wear and tear on the radar and have to replace those expensive parts less often if you're doing fewer rotations to scan stuff.
Are you just like the world's best coders, or is there a friendly GUI that you have on the DAOs and the cow to change all of these settings?
So they've evolved a lot again since originally, and the world's best coder used to be the inventor, which was Josh. But now with a lot of the radar stuff, we partnered up with NCAR, so the National Center for Atmospheric Research, and in particular, I'll shout out to Mike Dixon and Eric, and everybody else who's really been helping with a lot of the software and getting some of that stuff up and running. So yeah, I mean, it's all still custom stuff. I mean, trust me. they don't, I mean, we're very much asking for certain things. And certainly the evolution of the DAOs between Josh and, people like John Lutz, it's been a very big trade-off saying, no, this isn't going to work. I mean, this isn't off the shelf pieces. So if we can't do something that we want to do, people in one way or the other have been responsive and helping us develop how to do that. So it's pretty custom on how we do a lot of our things.
I'm just curious, like where's the funding for this coming from? Like what's driving the data? What's driving the need for the data and your operation, right? So you're providing this information to all kinds of the Weather Service offices and other folks around too. So give us some background on kind of the foundation of this project.
Lemonade stands? No. Well, we've already had Josh as a guest, so we could probably give you, more information than me. I mean, it's been piecemeal. I mean, there's been a lot of good partnerships and a lot of good investments. A lot of the science really is driven by, National Science Foundation funding for these various projects. I mean, Wintering Mix, the PERiLS project are funded primarily by the National Science Foundation. Collecting the data and supporting the collection of the data. sometimes NOAA or NASA is supporting that, but again, primarily National Science Foundation. In some lean years, I mean, we've done Discovery Channel. We've worked, with Discovery Channel, who's provided, some funding to do stuff. So that's been options. Right now, not right now, actually, as of a year ago, we've partnered with the University of Illinois. So I think that's a really good partnership that we're in the midst of. So helping, both doing the science stuff, but a lot of times doing the education is also equally important as training people on how to do and interpret radar data for the next generation. So, I mean, I think it's, mostly it's a lot of grant writing for most of us or other people writing grants. So
you can kind of flip the switch to some fun questions. So what is your appeal to storm chasing? What led you to get into storm chasing? What do you like about it?
So my initial answer is gonna be really boring. I just like getting out of the office and trying to figure out, how to collect data. But ultimately, I think it just drives back to the original reason that I, switched into meteorology. I'm sort of amazed that, and I'm not actually amazed anymore that I'm part of the process of collecting this data. I mean, initially it was sort of like, gosh, we don't really know this much about, what the winds are like in tornadoes or how tornadoes form, and then being part of, I mean, I'm not a modeler anymore, but being part of the, data collection process of it, I'm like, yeah, I understand why this is really hard. It's really hard to get out there and get that information. So yeah, so I think part of that's, driving me is that, oh my gosh, it's so challenging to do, and actually having a success or actually getting a bunch of minor successes to understand something is just cat butt. I love cats. Sorry.
Sorry, everyone. My
cat
insists on doing cat things right now.
Yeah, no, nothing makes me laugh more than a cat. But yeah, I mean, I think it's sort of the challenge of that. Like, oh my gosh, I'm like, can we, get this data set, or can we get enough of these data sets to really start, understanding these regions that are just hard to understand, hard to model, hard to link models to observations. And yeah, I just find it really challenging, but also really rewarding when you're getting data that you think actually is, advancing the field or advancing your understanding of what's happening out there.
Okay, now we did mention fire weather earlier before the show. We were talking a little bit about fire weather, but there's also tornadoes and hurricanes. So out of the three, which one, or maybe there's another type of phenomenon that occurs, some sort of weather phenomenon that occurs that you enjoy more than even those three, but which one do you enjoy the most out in the field?
Tornadoes, for sure. Hurricanes are miserable. There's no joy in a hurricane mission, except for the data that you're collecting, which hopefully, again, hurricanes are just miserable. I'm trying to put a positive spin on that. No, I mean, it's the first hurricane mission I did when I was a graduate student was 2004. And it was Hurricane Francis, and I'd gone out actually to do tornado missions. And I went out in June, and there was really no tornadoes, or there was one or something. It wasn't some fantastic tornado chase by the time I got out there. And Josh was still at University of Oklahoma, and they were looking for people to do hurricane stuff. And I'm just like, yeah, whatever, sure. I'll come out and do a hurricane mission, like not even thinking like what they're doing, what they're trying to study, what they're trying to understand. And and nobody really said much either. They're like, oh, it's like camping. And I'm like, okay. And I'm like, sleeping bag, pillows. I'm like, I don't know. I'm like, what do you bring to a hurricane mission? I'm like, no concept, So yeah, down there, I even remember too, I was in fluid mechanics at the time, and I had to like fax my homework in like before the mission, before the power went out. But then we went, and yeah, we parked on, we tried to get like these, now I know, we try to get these really forward locations. And I understand why. I mean, as the hurricane's making landfall, and as it's transitioning from its over water source to roughness associated with land, the dynamics are changing a lot from what's happening there to there. And what's happening really, you know, over the land is what you care about, because that's where it's making landfall, and those are the wind sweeps that are impacting people. So we try to get in these really forward locations, and I wasn't part of this at the time, you know, which means that you're scouting out sites that you don't think are going to go underwater, so you don't think are going to get flooded, and you also think are going to get pretty high winds, because you're trying to be in that part of the eye wall, the northeast part of the eye wall, that's making landfall. So we were on this road with a cliff down, and basically part of the cliff was eroding during the whole hurricane mission. It was nighttime. The 88D had gone out, and we were in one DAO, and then like the other team was in another DAO, and we could never get level the whole night, but nobody ever really wanted to get out because it's a hurricane. And, you know, so you're sort of like, why can't we get level? Because one of the legs that we level with is just sticking out into air. And we radioed to the other DAO for help, and we're like, hey, like, we can't get level, like, da, da, da. And they're just like, we're on fire, we can't help you, bye. So they had like some minor, you know, little saltwater fire going on. And then the next morning, and somebody in the DAO, and I mean, I was probably like, oh, this is horrible. I'm sure there's some video that was just terrible of me. I remember somebody's like, hey, do you want to like operate the radar? And I'm like, no, like, this sucks. And then somebody opened the door in the middle of the hurricane, like torqued the whole door, you know, like, you know, because you open it, but then it torqued out its hinges, and we're all like trying to get it shut, like out into the open air, and like the pillows and the notes and everything is just flying out. And yeah, the next morning we had to like tow the truck out, and we had to tow our support vehicle out. And it was, yeah. And I'm like, okay, I remember doing this. This is fun. I'll just do tornadoes. And I made a joke. I'm like, I'm never doing bridges, barrier islands, or beaches. So I actually didn't do hurricane missions for a while after that. I'm like,
How can our folks follow you on social media? I know you have social media, website. So here's your time to promote all that.
yeah, I could promote it, but then I won't really check it. The Doppler on Wheels, I think it's just at Doppler Wheels, Dow Wheels. I don't know. This is really good. We're really not into promoting.
But too busy for Twitter. She's like,
no, it's just. But we do try to like talk about the projects we're doing and the data we collected with the @DAO website. And the University of Illinois Atmos has an @thing. God, I need a media person, and I have an @thing. But I would probably recommend either, you know, @DAO or UI Atmos to see what we're actually up to.
Thank you, Karen, so much for joining us. And we definitely look forward to watching you out in the field this spring during the PERiLS project, and looking forward to the data that's being taken in on how to better forecast QLCS tornadoes. We appreciate you all watching and listening here on the Carolina Weather Group. We'll see you back here real soon.